So today we have Louis Morel presenting on even more remarkable contributions of women scientists, part 3. If you've been to parts 1 and 2, you know that Louis always promises an informative and entertaining presentation. So,
they were in the fall of last year.
yeah. Yeah. Well, you know, Louis holds a BS in biochemistry from McGill University and an MS in food science from Michigan State University. He worked in the food industry for more than 3 decades and contributed to the development of a food science course for high school students. So Louis, hit us with some fascinating feminist facts.
And there will be some. Thank you. So for those of you who may remember, last fall, I presented 2 installments of Remarkable Women Scientists. And maybe some of you missed those. And even if you were here, I'm going to start with a short refresher. I'll emphasize a point that I made then about women scientists. And I think that for those of you who were here, you'll remember it. So I'm going to start with a video clip. And I'm going to set this up. It is an excerpt from the book Lessons in Chemistry, and I'll talk more about that in a moment. And the scene in this televised version starts in a cafeteria. 2 chemists are sitting at a table, one man and one woman, Calvin and Elizabeth, and they're talking shop. And they're done eating, they leave to go back to their workbenches, and as they exit the cafeteria into the hallway, the conversation continues about Elizabeth's work and how it's not being recognized. Calvin knows this. Calvin is a prominent chemist who people think will be a nominee for the Nobel Prize, no lightweight. He recognizes her work, but nobody at the institute where they work really recognizes hers. Remember, this is 1962. So I want you to pay attention to the conversation that goes on in the hallway as they exit the cafeteria. There will be 2 important parts that I will emphasize afterwards. So let's start with this.
It is a bit of a chicken and egg situation, but if you consider Occam's razor, would nature choose a system that is more complex to create something less complex?
So RNA world theory.
Miss Ott, I'm going to be needing one of your special cups of joe to get me through this afternoon.
Right?
Of course, I would be much further along in my research if I wasn't making excellent coffee for mediocre chemists.
You're on the verge of a major scientific breakthrough. You need to talk to Donati.
I did. He said no.
That doesn't make any sense. Why?
Sex discrimination?
What?
Well, also politics and favoritism in general and fairness, but yes, mostly sex discrimination.
I don't understand. Why would anyone discriminate based on something as intellectually non-determinative as gender?
Calvin, how many female scientists can you name?
Madame Curie?
Exactly. Do you think that's just by happenstance?
I don't know. I hadn't considered it until now.
Of course, you haven't had to.
Because people fully appreciate your potential. This is me. Raise your hand if you'd like coffee.
For some of you, this scene may be all too familiar. So 2 important points here. 1, she talks about sex discrimination. I'll refer to it as gender bias, same thing. And you'll encounter that as we go along this morning. And also, if you ask the common mortal on the street to name a woman scientist, more often than not, the answer will be Madame Curie. And it stops there. It even did for Calvin. And by 1962, there were certainly other women who had made their mark in science, but even Calvin couldn't come up with anybody else other than her. So what happened to Elizabeth? As I told you, people didn't care for her work at first, didn't recognize how brilliant she was, and she was. And she's an unwed mother who, because of what she was doing for her daughter at school, became known as a great cook. And she was hired to host a cooking show on television. And she gave up her career to do that. And she injected the chemistry of food science into her work on air. And she talked not about vinegar, but she told the people listening and watching to add tablespoons of acetic acid. And she would add pinches of sodium chloride, not table salt. So anyway, she had a success. And if you haven't read it, I encourage you to read Lessons in Chemistry, written by Bonnie Garmus. And Miss Garmus has become familiar to us because of the book. And she must have made a bundle of money when Apple TV said, we'd like to televise your story. They turned it into a 6-episode miniseries. And that excerpt came from one of those episodes. Well worth reading and well worth watching as well if you have access. I want to bring your attention to a similar situation. We're not going to talk about gender bias per se here, but some of you may remember the movie The Major and the Minor from 1942. It stars Ray Milland, he's the major, and Ginger Rogers. The premise here is that Ginger Rogers' character named Susie, she is low on money. She has to travel by train, doesn't have enough money for the fare. So she dresses up as a young teenager. You can see by her getup here, trying to make herself look younger. And oh, by the way, Ginger Rogers was 31 years old when this was filmed. And she fools the ticket agent in the train station and buys a low fare ticket, gets on board the train, shares a compartment with the military officer. He's the major, she's the alleged minor. And he takes her to the training school where he's going. Remember, 1942, there's a military academy, and someone from the academy will take her to her final destination. But what I want to point out is one scene in which Diana Lynn plays the, I will say the, what's the right word? She would be a precocious, that's it, a precocious teenager, a well-educated teenager who happens to be the daughter of the commandant of the military academy. Ginger Rogers' character is going to spend the weekend there. She goes up to the room where the daughter, played by Diana Lynn on the far right, they have an exchange, but Diana Lynn's character is not fooled. This is no teenager in front of her. She knows this. And then Susie says, how do you know? In the camera shot behind the character played by Diana Lynn is a wall covered with bookshelves. And she says, it's biology. See those books behind me? All about biology. Someday I want to be like Madame Curie. So even in 1942, she was prominent and the first name that came to mind. Remember that in 1938, a lot of countries celebrated the 40th anniversary of the discovery of radium because it had become a part of cancer treatment by then. So in 1938, a big international hoopla about it. Here we are in 1942. The script writers did not miss the opportunity to add that in. And it's an amusing movie if you get a chance to see it. I want to mention here the Radium Girls. It's another book that you may be interested in. I'll mention this now. The book talks about what happened to the many women who worked in factories that attempted to, they incorporated radium, radioactive radium, into a number of products. She talks about specifically about people who worked in factories that made clocks and wristwatches because they tipped the hands of the clock with radioactive material so that it would glow in the dark. And you didn't have to turn on the lights to tell the time on your watch, or you could see it from across the room on a clock. The problem was, of course, that these workers, mostly women, were all affected and contaminated by the exposure to the radium. It happened in other industries as well. There are examples of lipstick that contained radium. And there were other products as well. So these workers were exposed to the radiation, and Kate Moore, a well-known author, discusses this in her book, The Radium Girls. And So remember this because it will be coming up again in a moment. It's tea time. Let's talk about tea. So here I have a tea bag in a wrapper, and you can find this in the office area behind us. I bring this up from, it's a product from the Tea Book Company. And this happens to be a mixture, proprietary mixture of tea leaves, of black tea and hibiscus and a few spices. And the marketing people chose to call this product Radiant Hibiscus. I hope they don't call it that because the tea leaves glow in the dark. But what really got my interest was the front part of the envelope. This is how the marketeers and an artist rendered the product Radiant Hibiscus. And I think it's worth dissecting this image. So if we start in the upper left, we see the name Marie Curie, which informs us that this woman here is supposed to be a likeness of Marie Curie in her younger years. If you follow underneath the board with the writing on it, there's a framed picture, 4 people. And the man has a beard, and what a coincidence, so did Pierre Curie, Marie Curie's husband. So we can imagine that that's Pierre, Marie, and below them, 2 daughters, Irene and Eve. So far, we're doing well. Go back up above that framed picture, and remember that Marie Curie died in 1934. How many blackboards were not black in 1934? So we have a green blackboard here. That wasn't introduced until much later after her death. On the board, at the very top, there's a T1/2 there, an equation, which I'll talk about later. And as you'll see, that is accurate. And then the PO and the RA are in rectangles. Those are the references to polonium, named after Curie's homeland, Poland, and radium, the one that she and her husband Pierre discovered in 1898, radium, hence the Radiant Hibiscus product and the Radium Girls. And the atomic numbers are correct. And underneath that, a couple more equations, which you will see in a moment, that have to do with some differential about N over T and so on. So aside from the color of the blackboard, which is not black, I'm okay with all this. Let's go to Marie now. You'll notice that she's holding a cup in her right hand. And because we know that she worked with radioactivity, in fact, she was contaminated because no one at the time in the late 19th and early 20th century knew how damaging those rays were. And she carried around vials of dissolved radioactive material in her lab coat pocket, as other people did. And yes, it did affect them. So here, she's the artist portrayed her as we're using a cup that is appropriately marked radioactive. There's a slight problem here that I have with the artist's rendition. What year did I say she died? 1934. That radioactive hazard symbol is called a trefoil. It was developed at the University of California, Berkeley in 1946. The Erlenmeyer flasks, one in her hand, one on the table, they're both glowing, and I get the idea there is radioactive material in them. Of course, the product placement is important here. Each one has a tea bag in it. And there's also a tea bag in the flask that is above on that tripod. On the bench in front of her, you can see a tea bag, and to the right of the tea bag is a medal. That is one of the 2 Nobel Prize medals that she earned. One in 1903 for chemistry and for physics, and 1911, that was for chemistry. And that's the one, you can barely see it. There's a red and blue ribbon to the right of that Erlenmeyer flask on the bench. So the 2 medals are portrayed. So by and large, and there are some certificates and awards on the wall behind her. So by and large, if you accept the premise here, it's a fair rendition, except for a couple of details that happened post-mortem, as it were. So if you are interested, this tea bag or these tea bags, there might still be some in the office in the background, but I thought that was rather interesting. So I want to get back to what's on the board. Those equations, they depict two things. First, the law of radioactive decay. And this is essentially one of the equations that was there written in a different form, but N is the number of radioactive nuclei. Lambda is the decay constant, and it's equal to the ratio of the decrease of the number of nuclei that are disintegrating over the number of nuclei that we started with. And A, and this was on the board, if you were paying attention, is the decay rate, and it tells us the number of disintegrations of the atomic nuclei per unit time. Seconds, minutes, fortnights, doesn't matter. And that equation, A equals lambda N, was on the board. So that brings us back to the top of that green blackboard, the half-life, T1/2. Well, their data told us that decay of radioactive nuclei is an exponential function, and it can be expressed by what you see on the board now. And knowing that and defining the half-life as being the period of time where the initial concentration, in this case, of radioactive nuclei reaches 50% of the original amount, the time it took to get there is the half-life. And the half-life doesn't just apply in physics. It applies in chemistry, in pharmaceuticals. The time that it takes for some substance to enter your bloodstream and to get to 50% of the original injection dose, for example, or ingestion dose, that's the half-life. So it's expressed by this expression. We saw this earlier. A equals the disappearance, the decrease of the number of nuclei as a function of time. And when you plot this on an XY graph, you get something like this. This is somewhat idealized, but it gives the idea. So in this case, if we had 800 disintegrations per second, for example, on the Y-axis, the vertical axis, that's where we start at time 0, and you follow that curve to where it is 400, 1/2 of 800, 400 disintegrations per minute, the time it took in this particular case is 20 hours according to the axis, the horizontal axis. So 20 hours is the half-life. And because the half-life is constant, it means that whatever is left at this moment, which happens to be 400, is going to take 20 more hours to get from 400 to 1/2 of that, to 200. And if you follow the line along this curve here, you'll see that from 400 to 200, we get to 40 hours total. So yes, every 20 hours, the concentration decreases by 50% more. So this half-life is ubiquitous in the sciences. So let's get back to where we left off. Some of you, perhaps all of you, were here last fall when I had sessions 1 and 2, and I concluded that today gender inequalities prevail in the marketplace. They may not be as pronounced as they were, but you know from your own experience that they certainly were, and you saw Calvin and Elizabeth talking about it, and it's still true today. However, there are more women than ever who are getting degrees in science and engineering and even medicine. There's still, however, a disproportionate number of men who have leadership roles, both in industry and in academia. And I'll show you a typical example of that in a moment. But there are some women scientists who have been very successful and some that are successful. And as this series continues to progress, you will find even more women that nobody's ever heard of that have contributed immensely to the sciences. So in that vein, I want to talk to you about the Fields Medal. No, not Marshall Fields. This is John Fields. John Fields was a professor of mathematics in Toronto. And in the 1920s, he was tasked with organizing the next International Congress of Mathematics. And he did that quite well. It was a resounding success. They even had money left over. And somebody said, why don't we use that money and have some medals made, and we'll give them out to some prominent mathematicians? What a capital idea. So they did that. They had the medals prepared. John Fields did not see the first award because he died in 1932, and they first awarded the Fields Medal in 1936. And then for some reason, of course, World War II came along, and they didn't actually award them until 1950. And they've been doing it every 4 years since then. And they had an endowment and a big donation. So they said, well, we could have more medals. So they give up to four medals every 4 years to prominent mathematicians. But there are requirements. One of them is you have to be under age 40. It's a little bit like the Nobel Prize. You have to be alive to get it. And that's partly why Rosalind Franklin was not mentioned when Watson and Crick got the medal for the DNA work they did, because ultimately she's the one who did the experimental work, who did the analysis that Watson and Crick borrowed, but she was dead by the time that they received the award. So there's a reason why she wasn't mentioned, but if she had been alive, would she have been mentioned? So speaking of Nobel Prize, this Fields Medal in the mathematics world is known as the Nobel Prize of Mathematics. And this is what it looks like. And I bring this up because that is not the head of John Fields. That is Archimedes. And his name appears in Greek on the medal. Don't strain yourselves. It's very difficult to read from these photographs. But trust me, in front of his nose is his name in Greek. This was designed by a Canadian named Tate Mackenzie, and his initials, RTM, appear on the left behind the neck of Archimedes, and the date is also near that border. It's in Latin, in Roman numerals, 1933. And if you flip it over, you have Latin text, which translates to pass beyond your understanding and make yourself master of the universe. That's the purpose of mathematics, isn't it? So where do they put the name of the recipient? On the outer edge. So imagine the rim, the ridge that goes around the medal. It's not stamped onto the medal, it's actually on the edge. That's where they put the name. But I want to draw your attention to Maryam Mirzakhani. She was born in Tehran in 1977 and a brilliant woman in mathematics. She published her first paper in 1999 at age 22, and she worked on geodesics. Geodesic is essentially the shortest distance you can have between 2 points on a curved surface. And if you may have heard the word geodesic before, perhaps in the context of a rather well-known American architect, Buckminster Fuller. He has designed many spherical buildings that are geodesics. And in fact, perhaps the most familiar one, the best known, is the geodesic dome that he created to be the US pavilion at the World's Fair in 1967 in Montreal. That building is still there. It's a very large spherical structure. It has been acquired by the city and turned into a learning center called the Biodome. So that's the geodesic dome that Fuller prepared. Well, she studied these things, and for that, she shared the gold medal for an international Olympiad. So brilliant woman, and she was recognized by the Fields nominating committee, and she won the award in 2014 at the age of 37. And unfortunately for all of us, she passed away from breast cancer in 2017 at age 40. So she qualified for the medal, and rightfully so. But what I want to point out, thinking about what Elizabeth said in the hallway and what I said during the last installments about gender bias and sex discrimination, Mirzakhani was the 53rd recipient of the Fields Medal, and the first 52 were men. So I suspect that there are other brilliant women mathematicians out there, but she was the first one to be recognized by the Fields Committee. Since then, one more has been recognized. So today, we'll talk about 4 women in particular. I'll start with, and I suspect that you have not heard of any of these, in spite of their accomplishments. So Maria Agnesi will be first up, then a duo named Pearl Kendrick and Grace Elderling, and finally Qian Xiong Wu. And I suspect, looking at your faces, that you may not be aware of any of these. So let's start with Maria. Maria was a phenomenon of the middle 18th century. She was born in Milan. Her family had made its fortune from trading silk. Remember, this is early 18th century. In fact, the family made its fortune at the very end of the 17th century and the early 18th. Her father, Pietro, had 3 wives. The first wife, 7 children. Maria was the oldest. He remarried twice after his first wife died and had 13 more children, 21 in total. When her mother died, the father, of course, had not remarried yet, so she was in charge of the children and her father. And then he remarried, and there were more children to take care of. But Maria was a prodigious young woman, and even at age 9, she was able to provide an hour-long oration on the rights of women to be educated to a group. Now, it was commonplace in those days for parents to display the talents of their children. Often, it was musical. My child can play the piano better than anybody else, and I'm going to invite people that I know to come and listen to my son or my daughter. Well, in this case, it had to do with oration. So she did that for her father, who showed her off to the others. By age 5, she spoke Italian and French. By age 11, she spoke 7 languages, including Latin, Greek, Hebrew, Spanish, and German. Tremendous aptitude for languages. And remember that there were no easy ways to learn these languages. You couldn't easily travel to Israel because there was no Israel. You learned Hebrew from the Jewish people who lived around you. You also could learn Greek from texts that were available to you, but there was no way to listen to recordings. So it was quite a task to be able to learn 6 additional languages from your own. And she was a very devout religious young woman, and she thought that she wanted to be a nun to help others and do charitable things, and her father was totally against it. So that did not happen. But she did continue to study religion, but also mathematics. She found that fascinating, and at age 20, she wrote some essays on natural science, which in those days they often referred to as philosophy, but they were natural science. And she talked in her essays about Newton, a contemporary, Isaac Newton's invisible force. That invisible force we know as gravity today. So she was precocious as well, age 20. She's already published this Propositiones Philosophicae. Her father wanted her to learn from the best. So he hired Father Rampinelli, a monk who had lived in Rome and in Bologna, more about that later, and hired him as a tutor to perfect her skills in mathematics. So he came to the house and he discovered how prodigious this child was at learning mathematics, to the point where he encouraged her to write about her knowledge on differential calculus, which was a new thing. Newton and the German Leibniz had come up with that earlier on, and she included that in her book later on. So this is the treatise that she is best known for. Instituzioni Analitiche ad uso della Gioventù Italiana. And there are a lot of things that are important here. For one thing, it was uncommon to write a scholarly book on any science in any language but Latin. But she chose to write about these analytical methods in mathematics in Italian for 2 reasons. She wrote the book allegedly to help her brothers, but it was also meant to be a comprehensive textbook. And she wrote this book in Italian for that purpose, more accessible to more people. So she did that, and she did it with her father's money. She assembled and printed the books in their own house, volume 1 in 1748, and the second volume the following year. Now, Admittedly, in her book, she did not provide any original mathematics. What she did was to collect all that was essentially known at the time to clarify modern mathematics. And that was important because it was a very disparate field at the time. You had to draw from various authors, various books. They weren't necessarily all available, but she was aware of British and German authors, and she collected all this information. She gave many examples. You will see one of them in a moment in her two books, and it was extremely popular. So Pope Benedict XIV took notice because he, before he was Pope, had an inkling in mathematics. So he understood the breadth of the work that she had done. And in those days, Catholic universities could only have faculty members that were appointed by the Pope. It could have been a formality, of course. The Pope did not decide necessarily that he, and no, there were not many women teaching, that that person could teach. The committee recommended it, and the Pope essentially sealed the deal. So the Pope offered an appointment of a professorship at the University of Bologna, well established since 1088, one of the oldest institutions in Europe and still active today. Well, she never accepted it. I don't know that there's any proof that she formally declined it, but she did not accept it. She never went. But interestingly enough, Maria's name appears on the roster of the faculty at the University of Bologna for 45 years, and she never showed up. And as far as I know, she never got a paycheck from them either. So this is the Pope, Prospero Lambertini, who at the time was perhaps unusual in that he had an understanding of mathematics. And he's the one who proposed that she teach at Bologna. But the legacy of Maria Agnesi is not so much the fact that she published this book, which was so instrumental in having her known, and it was useful for others. She's known today largely because of something called the Witch of Agnesi. And you don't have to be a mathematician to suspect that a witch is not a common mathematical term. So what is this witch? In her book, which has a lot of illustrations and examples, there's example 13, and there is this figure. And it shows a circle and a curve above it that touches the top of that circle. You can see point C on the perimeter or the circumference of that particular circle. And she was interested in the curve that goes around the circle. Now, she didn't create the curve. She just studied it because there were other luminaries who, before her, studied this curve. You go back almost 1 century, and the French mathematician Pierre de Fermat was the one who determined that it was a cubic bell-shaped curve, and he came up with a description of an equation for it. It wasn't until the 1710s that an Italian mathematician, Luigi Grandi, came up with a way to construct this curve, which I am going to show you in a moment. And even Isaac Newton studied this, but his work about this curve was not published until after his death in the 19th century. So what is it with this witch? She had called the curve aversiera, which comes from the Latin vertere, which means to turn, and she referred to this as others before her had, as a sine curve that had been turned, had been converted. So she used the word aversiera. Meanwhile, there's an English mathematician at Cambridge named John Coulson. And Cambridge was already prestigious. Coulson had a professorship there, well respected. He had translated one of Newton's books, who had written it not in English, but in Latin. Remember, I told you that most scholarly tomes were in Latin. So Newton wrote in Latin, and Coulson translated De Methodis Serarium and Fluxonium from Latin to English. And he hears about Maria's books. He feels compelled to translate them. So what he does is he learns Italian, and he becomes non-fluent in Italian. And we don't know the exact date of publication, but it was before 1760 because that's when Coulson died. And it wasn't published until the year 1801. But what did Coulson do that is so remarkable? He just translated the book, right? Well, the example on the left, the curve, is what was published in his book. It's a reproduction with a translation of the caption from Maria's text. And underneath that curve, you read, let the curve to be described be that of problem 3, called the witch. Where did that come from? The word aversiera was misinterpreted. He translated aversiera by mistake, which means wife of the devil. So aversiera with 2 V's is the wife of the devil, a she-devil, a witch. And that is what got published in the caption underneath this illustration. And it's stuck. To this day, we talk about the witch of Agnessi. So how do you build this witch? It's quite simple, actually. Well, it is a few centuries later, of course. So you start with a circle and you draw a line tangential to a top or bottom of the circle. We'll use the top here. And then once you've done that, you pick a point at the bottom of the circle. Here it's illustrated by the letter O as an origin, the letter O, and you draw a line from that point to a point on the far left of that tangential line to point P. So now you have a line from O to P, and it crosses the circle at point Q. You draw a vertical line from point P downward, and where it intersects the line between Q and R, you put a blue dot. So now you have a point. And you do this again and again, such that you create all these lines that cross the circle at different points. And you put a blue dot where the 2 lines, the perpendicular lines, intersect each other. And if you draw enough of these, you get a continuous blue curve like this. That is the witch of Agnessi. And to convince yourself of one more thing, knowing that it is a cubic equation, and there you have it in the left side, it's a relatively simple one, and you can go home and do this for yourself, and you'll find that if you use the diameter of a circle for the value of A in this equation, you will actually get this series of lines, each one of them being a witch of Agnessi. So it's a cubic function, and you can do it for any diameter of a circle, and it works quite well. Now, you can also imagine something if you want to be a little bit far-fetched here. You see that the uppermost curve, just above the number 15 arbitrary units on this particular graph, if you were to extend that bigger and bigger, you might actually have a more pointed curve, and it would look like the hat of a witch, maybe? Maybe. It is October, after all. So what did she do with the rest of her life? After her father died, now remember there are 20 siblings now, and her father is dead. She's the oldest one. She gave up mathematics. She had a lot to take care of, but she even declined an offer from the University of Turin to review a paper by the French mathematician Lagrange. Some of you may know him. His work is used prominently to this day. She didn't even want to do that. Not teaching, just reviewing a paper. She declined the offer. Instead, she wanted to devote the rest of her life to do charitable things. And you may remember I had a slide that was titled Religion and Mathematics. Well, she was a devout woman, and she wanted to do more for the sick. Well, she did that. She, in fact, impoverished herself. Her father was dead now. There was no income to speak of. And she turned her own home into a refuge for sick people. When she had been approached by the Pope after the publication of her books, she received not only the appointment to the University of Bologna, but the Empress of Austria, as I recall, gave her some jewels in recognition of her work. And I believe there's an account that suggests that the Pope had provided some jewelry as well. She sold those to get money to help the poor. So as I said, she impoverished herself. As she aged, she grew deaf and blind. She lived to be 81 years old. And in the middle or late part of the 18th century, 81 years is a pretty long lifetime for most people. So that was rather uncommon. But she died a pauper. There was no elaborate monument erected for her at all. So Maria Agnesi has, to a large extent, fallen into obscurity, other than her work on the witch of Agnesi, which is not a witch at all. However, there are some tributes. In 2018, to mark the tercentenary of her birth, back in 1718, both Italy and Vatican City issued postage stamps in her honor. So the one on the left is quite easy, and now you can recognize that famous illustration that shows the curve, the witch of Agnesi on the left stamp from Italy. And it shows a portrait of her. The one on the right from Vatican shows three things. One, it emphasizes her devotion to God as she is kneeling and praying. On the floor to her right, there are a few papers. If you were to use a magnifying glass, you would easily see that that illustration is on the top sheet of paper. The Witch of Agnesi is there. And on the wall behind her, or at least in the background, is a simplified version of the equation that I showed you, that cubic equation. So all this is represented on these two stamps. And I want you to make a mental note that these two stamps inform us about the work that she's famous for. I'll come back to that later on. So that's how Maria Agnesi was celebrated in postage stamps in 2018. I suspect that few people here have ever heard of Pearl Kendrick or Grace Eldering. I can see from your puzzled faces that I'm right. Well, let me get to your attention. These two women became famous for the work that they did in Grand Rapids, Michigan. Kendrick and Eldering grew up worlds apart, 2,000 miles apart. Kendrick was born in upstate New York at the end of the 19th century, and Eldering was born in Montana just to begin the 20th century. Kendrick studied in New York State. She got her first jobs there, as you will see in a moment. Meanwhile, Eldering was a girl from Montana, and she studied there, and she got her first job there as well. But they did have some common interests. Remember, this is the beginning of the 20th century, but they both have interests in bacteriology, a new emerging science. Bacteria were known, viruses were not by the time that they were doing this. They were both women who had meticulous practices. They were detail-oriented and bright women. And both of them together, as you will see in a few minutes, were able to involve the communities to get maximum participation and ultimately to get some very desirable results. The Depression was devastating for a lot of people. And in Grand Rapids, as you might expect, and you may be aware that it was no exception there that companies went under. The furniture making business almost collapsed. Banks closed. People were impoverished and unemployed. There were soup lines. But at that time, for women and for men, public health jobs were available, and they were a good entry level for women to get into that particular field. I have a statistic here that in 1932, nationwide, 6,000 people died from pertussis, also known as whooping cough. And pertussis killed twice as many children as polio and diphtheria combined. So it was definitely a serious problem that they were dealing with. And one of the problems is that it was difficult to diagnose. So it started out mildly, and by the time it was diagnosed, it had progressed so much that there's not much that they could do for the person who was stricken, usually a child. So neither one of these women had set out to work on studying and perhaps eradicating pertussis, but that's what happened. And they also, in the course of doing that, perfected research methods that became well documented, well known, and praised by people in the community, the scientific community. So the two of them had somewhat parallel paths. Kendrick, interestingly enough, got a liberal arts degree from the University of Syracuse. Meanwhile, Eldering got a degree, a major in English and a minor in biology from the University of Montana. And both of them started their careers with their degrees teaching. Kendrick taught in New York State, taught high school science at first, and Eldering taught elementary school. Neither one of them was totally pleased with that. Kendrick went back to school. She lived in New York State, remember? So she went to Columbia University and got a graduate degree in bacteriology while she was teaching and while she was promoted to principal of the school. And she got that degree at the time. And in the meantime, because Eldering was not thrilled with being a teacher, she also went back to university and got a degree in bacteriology. So here's a common trait that is appearing. With her lack of interest in teaching, Kendrick discovered that she wanted to be in the biology field, and she got a job at the New York State Department of Health. And a visiting scientist who was a public health officer from Lansing, Michigan, discovered her in New York, and he was interested in her work, and he offered her a job. So she came to Lansing to work in the laboratory of the State of Michigan Health Department. While she was there, a number of things happened. The State of Michigan opened a new branch called the Western Branch in Grand Rapids. And that was in 1926. And she had proven her mettle, and she was the one who was appointed to lead that effort in Grand Rapids. While she was there, she went to Ann Arbor and got a degree in serology from the University of Michigan. And she also went to Baltimore and got a degree from Johns Hopkins, her doctorate in science. And in 1931, she went back to Ann Arbor and she got a degree in pathology, all while she was working for the state of Michigan. Meanwhile, Grace Eldering is in Montana, and she has accepted a job as an unpaid volunteer. It's supposed to be for 6 months. So she hops on a train and she goes to Lansing and starts working in the lab there. And that's how they met. And in 1932, by this time, the Western branch of the State Health Department was doing some research on pertussis. And that's where Grace Eldering steps into the picture. She became a part of Kendrick's team. Later on, during the war, Eldering went to Johns Hopkins and she too got her doctorate in bacteriology from Johns Hopkins. So they do all this work on pertussis, which I will discuss in a moment. And later on, the University of Michigan attracted Kendrick, and she went to Ann Arbor and she taught at the School of Medicine there. And that's when Grace Eldering took over the top position at the Western branch when Kendrick went to Ann Arbor in 1951. So pertussis was a tremendous challenge to physicians and to scientists. It is caused by a bacterium, and I'll introduce you to the bacterium in a moment. It attacks specifically the respiratory mucosa. So that's one thing, but its effects are not just respiratory, they can be felt in other parts of the body as well. It's difficult to diagnose, as I said, until it has progressed to the point where the stricken person is having difficulty breathing and makes a whooping sound, hence the name whooping cough, but that is pertussis. The man on the left is a Belgian named Jules Bordet, and he's the one who identified with his brother-in-law, Octave Jean-Gou, they actually identified the bacterium that causes it, and they were able to grow it in an artificial culture. That happened in 1906. So that was a move forward, obviously. Within 10 years, a lot of American companies, that some of which you've heard of, actually had what they thought was a vaccine available for pertussis. There was one problem. None of these actually worked. So they were not producing a vaccine that had any effect on the disease. So Bordet won the Nobel Prize in 1919, but it wasn't because of his discovery of this bacterium or the fact that he could actually grow it. It was for his study of alexins. And alexin is not a term that is used very often these days, but an alexin is a protective compound that is found in the serum of your blood that actually can kill microorganisms. That's why he got the Nobel Prize in 1919. And there is an electron micrograph of the rod-shaped bacterium that causes pertussis. Now, from this, you can't tell a whole lot, but when you study it, you find out that it can actually secrete a number of toxins, and they are nasty for the respiratory mucosa. Jules Bordet himself was honored on some postage stamps, and not surprisingly by Sweden, because the Swedes have taken it upon themselves, since they give out the Nobel Prize every year. They have taken the liberty of putting the recipients on a number of their postage stamps. This one on the left is from 1979. It marks the 60th anniversary of the award of the Nobel Prize to Bordet. And you can imagine that the glassware in the image here is reminiscent of what he might have been using in a laboratory around the turn of the 20th century. So the image is certainly, to me, much more accurate than the one that we have on the wrapper of the tea bag. The one on the far right was issued more recently, 2016. He was a Belgian citizen, and here he is honored as one of many Belgians to have received a Nobel Prize in any of the 5 categories. His, of course, was for medicine back in 1919. I point to the one in the middle for 2 reasons. It is from the Ivory Coast, and it was issued in 1978. And I want you to note 2 things. It's a Jules Bordet portrait from his younger days on the left. Above him in the middle, that black circle with white polka dots, that's meant to be a petri dish. And those white dots are colonies of the bacteria growing in that particular dish. Allegedly, those of Bordetella pertussis. Bordetella was named after the Belgian scientist Bordet. And what really caught my attention is not the pastoral scene, which suggests that if you've been vaccinated, you'll be able to, as a child, you'll be able to play with a butterfly in your hand in the fields. What got my attention is that whoever designed this stamp got it wrong, because at the very top, upper right corner, it's written that he got the Nobel Prize for Medicine in 1920. But we all know that the year was 1919. So you can't believe everything you see on postage stamps. Back to Eldering and Kendrick. So there they are in Grand Rapids. It's the 1930s. It's the Depression. There are people who are out of luck, and there are diseases going around, but the public health department in the state of Michigan is adamant. We are going to do all we can for our citizens. And in fact, in the 1920s, the Michigan legislature had set aside funds for that very purpose, to actually do research in the health department. And Grand Rapids had a tremendous history. Among all the cities in the US with a population above 5,000, Grand Rapids was the only one who did not have a single death from diphtheria in 1928. Part of this was its monitoring programs for water quality, for example, and also the education of the public. So Grand Rapids was very proud of what it had established in the city. So what Kendrick did was to recruit physicians. There were about 24 of them in the Grand Rapids area who participated with her in gathering data. They saw the patients, they knew what their disease was, or at least they had symptoms they could document. She also recruited the Visiting Nurses Association to go and collect samples. And how did they do this? In those days, they had what they called a cough plate. So you can imagine some circular device that the nurse or a physician would use, and the person would cough onto it and would be exhaling and projecting whatever was coming out of the lungs, and then the surface of that cough plate could be analyzed. This became important when there were indeed some outbreaks, because they could document that this patient, we've cultured the bacteria on this cough plate and we know what it is, but they also instituted quarantine standards. And for pertussis, you had to be at home for 3 weeks, preferably 4. You had to, and this will be familiar to you, you had to prove that you were negative on 2 cough plates taken days apart, reminiscent of what we were doing with SARS and still are doing with SARS-CoV-2. Even in this post-pandemic era, you have to prove that you're negative twice. The same thing was being done then in the 1930s. Now, what was interesting is they continued to do this work in the 30s. They did animal studies using mice. They published quite a few papers on this particular study of immunization, first identifying what the problem was, then developing a vaccine. And when they did that, because they had a couple of dozen physicians participating in the study, they were able to distribute the vaccine to these physicians who then could inoculate their patients. The trial lasted for the better part of 3 years. They recruited 1,600 children. They were all matched statistically for gender, age, and the district where they lived. And it turned out that of all the children vaccinated, 712 of them, only 4 came down with pertussis, suggesting that the method that they had perfected, understanding the phases that the bacteria go through, they were able to attenuate the bacteria and then use the components as part of the vaccine, inoculate the children, and only 4 of the 712 actually developed the disease. Meanwhile, of the almost 900 control children, 45 of them contracted the disease and went through the whole hoopla of having the disease and had to be cured afterwards. So their work that was published gained them not only national, but also international acclaim. And one of the reasons was that they developed methods that had not been standardized beforehand to collect data in the field studies. There's a tribute to these 2 women in Grand Rapids, and it's tucked away, and you may not have seen it. On your right is an image of this 7-foot tall statue. The woman in the middle is actually Pearl Kendrick, and to her right is Grace Eldering, and this statue was made or unveiled in 2019. To the left, with the microscope tucked under her arm, is their lab assistant, Lonnie Clinton. And the sculptor is J. Hall Carpenter, who used over 1,400 pounds of bronze to sculpt these 3 women. Interestingly enough, and this is good context, across from this statue, there is a statue of 2 young children. And that reminds us that pertussis actually struck mostly children at the time. So they're part of the equation as well. And interestingly enough, this is on the campus of the Michigan State University Medical Building. And it happens to be looking at Michigan Street, which is known, that stretch of Michigan is known as the Medical Mile. So that's where you might see this statue called Adulation, the Future of Science. And that's the tribute to Kendrick and Eldering. This brings us to our last scientist today. And I suspect that, once again, you're not familiar with Qian-Xiong Wu. She was born near Shanghai in a small town named Liu in 1912. Her father was an engineer, her mother was a teacher, and Qianxiang was very fortunate because her parents valued education, but more than that, they valued education for girls. And in many parts of the world, that was not a value that was practiced by too many people. Her father had participated in the revolution that occurred in 1911. And that revolution, won by the people, essentially marked the end of the Qing dynasty. And there had been imperial rule in China for about 2,000 years. And that was the end of that. So he was a part of that revolution. And it gave the people a lot more power. And what he did, he opened a school for girls. But unfortunately for Qianxiang, she was a bright girl, and by age 9, she'd already done all that she could do academically at the school that the father and mother had opened and operated. So they sent her to a boarding school, one that embraced Western ideas. The problem for Qianxiang here is that this particular school was putting her on an academic path to turn her into a teacher. Might have made her mother proud, who was also a teacher, but that's not what she wanted to do. She was interested in the sciences. So while she was at the boarding school, of which she graduated with honors, by the way, she taught herself mathematics, chemistry, and physics. Yes, she was a bright girl. She did study English, never mastered it, even though she did live much of her life in America, as you will find out. And in 1936, she enrolled in mathematics at the National Central University in China, but she really wanted to study physics, and she switched to that particular major after that. After she got her degree, she got a teaching job at some provincial university in China. The next year, after she had been teaching there at that university, she got a job at the Chinese National Academy of Sciences, and she started work with other people on X-ray crystallography. This is the 1930s, early 30s, so it's pretty much a new field. It won't come into its own until the 1940s, and as I mentioned earlier, Rosalind Franklin, the British crystallographer, she's the one who in the late 40s actually put it on the map, as she deduced the structure of DNA that Watson and Crick popularized afterward. But while she's at the Chinese National Academy of Sciences, she feels stifled, and another woman member there suggests to her, why don't you go study in the US? They don't have the facilities here for you. So she did. She won a scholarship from the University of Michigan. Why did she want to go to Ann Arbor? For one thing, there were a lot of Chinese students in Ann Arbor at the time, and she won a scholarship. So she set sail, literally set sail for America. Her uncle, who was the first one to establish long-distance bus company in China, made a lot of money, and he was able to subsidize her trip to America. It took 4 weeks for her to get from China to San Francisco, and she arrived there in 1936. So she is essentially supposed to be on her way to Ann Arbor. It's Michigan or bust, right? When she got to San Francisco, she went to Berkeley nearby. And there she met Ernest Lawrence, who had invented the linear particle accelerator known as a cyclotron. And for that, by the way, he won the Nobel Prize in 1939. The cyclotrons around the world, and there's one in East Lansing in Michigan State, they actually can produce radioactive elements artificially, and they can be studied. So Ernest Lawrence did that, and you might know his name if you're familiar with the Lawrence Livermore Laboratory in California. But also there was another dude teaching quantum mechanics at Berkeley. His name was Robert Oppenheimer, and you may have heard his name. The photograph on the upper right is taken from the campus of Berkeley, looking across the bay. And she was so enamored with the staff at Berkeley that she said, I'm not going to Ann Arbor, I'm going to stay here. So she never went and took advantage of that scholarship at the University of Michigan. But there was plenty of turmoil in those days. The Japanese invaded China the year after she left. When she said goodbye to her parents in 1936, it turned out that she would never see them again. And you'll learn why in a few moments. That was the last time that she actually physically saw them. Tens of thousands of Chinese people died during that invasion by the Japanese. Her parents were not among them, but it was a period of turmoil. But that wasn't all that happened. Of course, World War II broke out. So now there's more turmoil in Asia and the entire Pacific hemisphere. And she can't communicate with her parents again until after the war in 1945. So she stayed at Berkeley. And while she was there, she met another graduate student, also he was a Chinese American, Yuan Qiu Liu, and he Americanized his name to Luke Liu. They would marry a few years later in 1942. There was a man on staff named Emilio Sagre who discovered rubidium, element 37, and he would be honored by the Nobel Prize later on. He recommended her for a fellowship at Berkeley. But did I mention gender bias once or twice today? If I didn't, I can tell you that the recommendation was rejected by the university. Okay, A, she's a foreign student. B, she's a woman and she's Asian, and maybe there are better candidates that we can give scholarships to or fellowships to. Nevertheless, in 1940, Berkeley awarded her with her doctorate in nuclear physics. And her research focus, which was not exclusive here, but her research focus was on nuclear fission. And that was an emerging field at the time. Well, nuclear physics in general was an emerging science. So she was on the cutting edge, literally, of that particular field. And also, when she was a research assistant at Berkeley, doing her own research work for her doctorate, she also did some work on radioactive xenon-135. Make a mental note of that. It'll come in handy in the quiz. So she worked on xenon, which was important. Xenon is one of those rare elements, one of the noble gases like radon, for example. But xenon-135 has radioactive properties that she studied. Luke, her husband, was offered a job in Princeton. He was also a brilliant man and sought after. So RCA, remember this is wartime, and Nipper the dog and the Recording Company of America, RCA, are doing other things with their scientists. And they're inviting Luke Lee to go to Princeton to work on designing instrumentation and better radar devices. Radar is a brand new device, and it's primitive, and it's going to be very useful in the fight against the Nazis and the Japanese. So he accepts the job to go to Princeton. So now he's across the country. Qian Xiang decides, I'm going to go east as well. She took a job in Massachusetts at Smith College. She wasn't very happy there, but they could meet in New York City on weekends. So their long distance relationship was not as long as if she had stayed in California. When you think of the Manhattan Project, whether you think about the events that happened at the University of Chicago or at any of the other government labs or at Los Alamos, the name of Qianxiang Wu is not the first one that comes to mind, if at all. And there was a problem in one of the government research centers where one of the nuclear reactors kept shutting down. And you might know the name Enrico Fermi. He was told by one of his colleagues that he should ask Miss Wu what might be happening. So she was known by some as a force in this area, and possibly because somebody knew that she had worked on nuclear fission, maybe she would be able to help them. And indeed, she did. She did go to the nuclear reactor, she analyzed the situation and determined correctly that the problem was contamination by xenon. Did I tell you to make a mental note of that? It turns out that she had studied xenon, and the cross section of the xenon atom is such that it has a tremendous affinity for electrons. And they absorb those that are in a chain reaction, a nuclear chain reaction, and they essentially quench the reaction and bring it to a screeching halt. So it was the worst nuclear poison that you could have in the reactor. So based on her analysis, the engineers figured out ways to avoid this from happening. So she was well known in those circles for providing a correct answer. She later joined formally the Manhattan Project at Columbia University in New York in 1944. And she developed instruments to measure radiation. And what was, I think, more important is that she also was able to develop a method to discern uranium-238 from uranium-235. Why? Only the 235 version is the one that we want for nuclear fuel. We don't want contamination. We want a purified uranium-235. So she worked on that and was successful. And I want to point out that what she did in the 1940s should have applied in the 1980s and 90s. The photograph on the left shows you one of the reactors at Chernobyl in Ukraine after the meltdown. Totally devastated. Well, it turns out that one of the factors that caused the destruction of this reactor was the buildup of xenon-135. And the scientists and engineers did not account for that when they did their testing of the turbines and the reactors, and it caused the meltdown of Chernobyl and all its consequences. So the work that she did some roughly 40 years earlier was imperative, and they didn't take that into account. She had a chance to go home, and so did Luke, her husband, in 1945 after the war. The Central University where they had studied was beckoning them to come and teach there. But her father said, don't do it. His premise was that if you come to teach in China and you want to go back to the US, they will not let you back in. So she declined the offer. They did not go back to China to teach. She stayed at Columbia in New York, and she worked on beta decay. The beta decay refers to the disintegration, the type of radiation that occurs that is emitted as an atom disintegrates. And so much so that she became an expert in that area, and you'll see why in a moment. So she did not go back to China in 1945. She is known as an experimental physicist, and that, at least in one case, was her downfall, as you'll find out. So she was able to demonstrate experimentally a number of things that theoretical physicists could do on a blackboard. Yes, they were black in those days. And she was able to demonstrate that they were right in most cases. You've heard of Enrico Fermi. Well, he had predicted the speed of an electron that was involved in this kind of beta decay. Well, she was able to prove that he was right. She was the experimenter. He was one of those theoretical physicists. She was able to develop the experiment necessary to do that. But her biggest achievement experimentally was investigating the law of parity. There was a huge question at the time whether or not these subatomic particles, and remember that we know today that the physics of subatomic particles don't exactly behave like the ones that Newton talked about. So at the subatomic level, does nature distinguish between right-handed and left-handed electrons? When they emit from the atom, does it matter? Is it a 50-50 chance, like flipping a coin, that when it emits from the atom, it's going to be in one direction or the other? There were two theoretical physicists, also Chinese Americans, Wang and Li, who believed that it was a 50-50 chance. But they couldn't prove it because they too worked with a blackboard, but not experimentally. So they came to her and they said, can you devise an experiment that will prove one way or the other if this law of parity exists? Does nature recognize them at the same frequency, or is one preferred over the other? So she devised an experiment, and it wasn't easy, but in 6 months, she had successfully recruited the National Bureau of Standards because they had the equipment she needed. She used cobalt-60 atoms, and she had to bring them to near absolute zero. That's zero, negative 273 Celsius. And you can only achieve that with a partial vacuum. You can only do that with special equipment. The NBS had the equipment. She went there, and the idea was to align these cobalt atoms as best as possible. And you can do that if you can slow them down near absolute zero temperature. So she did that. And did the atoms align? Yes. And is there symmetry or not? When they took the data from the experiment, they saw that it was preferred for the atom to emit the rays in one direction and not the other. It wasn't all of them, but it was not 50-50. There was, in fact, asymmetry. There was no parity. So that's the person who described this. And she became very well known for this, for solving this problem and becoming an experiment. So Li and Wang, who had proposed the experiment, well, actually they proposed the theory, she did the experiment. They won the Nobel Prize in 1957, but Wu was never mentioned. Why was she not mentioned? It's possible, and I'm surmising here, this is pure speculation. She was Asian. She was a woman. So it's quite likely that she was disregarded because of that. So they won the prize, and she did not. She wasn't done. In the 1960s, she was very active. You may have heard of Richard Feynman, the physicist, and Murray Gell-Mann. They had an hypothesis about beta decay and weak nuclear forces. There are 4 forces in the atom. The weak nuclear forces are the weakest, most difficult to study. They had this hypothesis. She proved them right. She was a tremendous experimental physicist, better than most. And she published her book in the middle of the 60s on beta decay. So here we are now. She's very famous. She's accomplished a lot, and she hasn't been able to go back to China. And by then, of course, it's under communist rule. She can't go back. So she saw her parents in 1936. Then, because of the war, because of the invasion of the Japanese, didn't talk to them until 1945, did not go back to China because her father said, don't come back. You'll never be able to go to the US again. And she didn't do that. And her parents died, and she never saw them again. She got a lot of honors, including being elected to the National Academy of Sciences in this country. President Ford gave her the National Medal of Science. She had a lot of honorary degrees. And there's even an asteroid named after her. Time magazine initiated a project in the not too distant past to illustrate 100 women of the year. And you may remember when Time in its heyday, they always had the man of the year. There were very few women who made the cover as woman of the year. So in recent years, they tried to do this. They commissioned some artists to draw covers of the women they selected and to make them look like the covers of Time's heyday of the 1930s and 40s. So this one was of Qian Xiangwu, was drawn by Jennifer Dionisio, and it is meant to be Woman of the Year for 1945. And by the way, there was no Man of the Year in 1945 as the war was ending. So this one is part of the 100 Women of the Year that Time magazine has put together. The US Postal Service issued a postage stamp, and I don't know how many of you actually purchased this stamp when it was issued in February of 2021, or how many letters came into your mailbox franked with this particular postage stamp. And I'm going to guess none. In spite of the fact that the United States Postal Service issued a few million of them. Now, I have a bone to pick with the designer of this particular postage stamp. Qianxiang Wu is not a household name. And it says nuclear physicist. That's good. Now we know what she did for a living. But what did she accomplish? I do not know if the designer of the stamp actually thought about how to illustrate what she might have done. Could there have been a cyclotron in the back showing that she did experiments with it, or something else? Possibly. Was it dismissed? I don't know. But think about the stamps that I showed you for Jules Bordet. In one case, there was glassware in the lab. Another one, there was a petri dish showing colonies of bacteria growing. They were related to his work. Could the designer of this stamp not have come up with something to show that she did what she accomplished? So we have a great photograph of this woman who, by the way, wore Chinese garb most of her life, including in the US. And she's portrayed that way in this photograph here as well. So none of her accomplishments was actually portrayed on the stamps. And that's it. Are there any questions or comments that you would like to share? And if so, Linda will bring the microphone to you so that the people in cyberspace can hear you.
You mentioned an atom disintegrating.
Yes.
Describe what you mean
Sure.
by disintegrate, please.
Sure. So it's the simple purpose. You've got an atom. It's got protons, neutrons, and electrons. If it's radioactive, it's going to emit some rays, and it also will lose part of those particles. So it's disintegrating because it's converting itself from what it is. And as it loses an electron, it becomes another element. So that's how you get polonium, starting with uranium. You start out with enriched uranium and you put it into a chain reaction, you obtain polonium as a byproduct, if I'm not mistaken. Yes.
I thought that it was the number of,
Neutrons.
oh, okay, protons
Protons and
and
neutrons.
neutrons in the
Yes.
nucleus that determine the element.
Yeah, well, yes, but the number of electrons can too.
I
They're
did not know
characteristic.
that.
But if you lose a neutron, the atomic weight will change.
Right.
Yes, okay. So you actually, it could be that it's the same element. For example, if I talked about uranium 235 and 238, so the number of neutrons is different.
Right.
And you have different properties for those two uranium atoms. But
Right.
you can also convert uranium into another element as it loses an electron or two.
Okay.
Okay. There's a question, one question here in the front, Gordon.
Does gender bias have a half-life?
Is that expressed in decades, eons? It's a good question, and I don't know if you have witnessed, perhaps in your own lives, perhaps in your children's lives, as you or your children progress through their careers, if there have been discussions about equity in salary, same job, man, woman, there's a range of salaries, usually entry level. Does the woman's salary progress as quickly as the man's? Does it start at the same point in the range as it does for a man? I know for a fact, my experience, that isn't always true. There might be some organizations where there's more equity than others. Is it better today than it was 20 years ago? 30 years ago? I'm not so sure. There's still, interestingly enough, that bias that Gordon reminded us of. And is it less likely when a company is led more by women than by men? There are a few of those companies, and there are a few big companies. The first one that comes to mind is Hewlett Packard. Hewlett Packard had a woman CEO for a while. Did anything happen to salary equity based on gender while she was in charge? I don't know. So these are interesting questions, and you may have personal experiences from yourself or perhaps a child as he or she went through his or her career talking about that. So I don't know the answer to that, Gordon, sorry. Though I'm sure there are some people who study these things that probably would have an answer, at least showing us a trend if there is one. Anything else? I'll invite you to come back next week for part 4 of this series. And I hope that I bring to light the lives and the accomplishments of a few more remarkable women scientists for you.
Okay, Louis, thank you so much.
Thank you.